Chuck, I got another explainer for you.
All right. I'm always up for a good explainer.
It's been a while since I've blown your mind.
Okay.
So I don't know if this will do that.
Okay.
We're going to talk about the Maxwellian distribution of velocities.
I don't know if you blew my mind. I'll tell you this myself. What the hell? Wow. The Maxwellian distribution of velocities.
Yeah. Okay, so you're going to hear me out?
All right. Let's do this.
You want to hear me out?
I'm going to hear you out.
Okay, so watch. So
wait a minute. I got to wake up. Okay, here we go.
Okay. 19th century physicist.
All right.
James Clerk Maxwell. Middle name spelled Clerk, but I think it's pronounced Clark.
All right.
James Clerk Maxwell.
Maxwell.
Towering genius of classical physics.
Wow.
Okay?
That says a lot.
There's a set of equations that describe everything and our entire understanding of electromagnetic forces.
Really?
It's called the Maxwell equations. It's the same guy.
That's the guy.
Yes. Here's something else he did. He discovered a distribution of velocities that bears his name. We learn that, let's take a gas, for example. What is the gas doing? Well, they're particles that are vibrating and hitting against each other at all times.
It's like a little mosh pit.
Yes. Mosh pit. There they go. Depending on the temperature of the gas, if you raise the temperature, what would you imagine the mosh pit will look like as you begin to raise the temperature?
A little more violent.
A little more violent.
Yeah.
Yes.
Yeah. It's like somebody put on death metal.
Okay. More violent.
Right.
Okay. People moving faster.
Right.
All right. Stay with me.
Okay.
Okay. I want to make a plot of how many people in the mosh pit are moving at whatever given speed I'm asking about.
Okay.
Okay? That's called a distribution.
All right.
Is anybody going negative speed?
I don't think so.
The answer is no.
No.
So whatever is happening, it's got to hit zero, okay? Nobody's going negative.
Right.
Okay? All right. Now, some people aren't moving very fast.
Right.
There aren't many of them. So there's a few people down here. As you go to people who are moving faster, you have more and more of them. You're going to reach a peak where now the most number of people are moving at this speed.
Right.
Then it drops off. Fewer and fewer people are moving the fastest, almost by definition. Everybody can't be fastest.
Right.
Only some of them are moving the fastest.
Right.
Those are the most violent among them.
Yeah. It's a guy you don't want to dance next to.
Correct. So he figured this out for mosh pit. No. But the mosh pit is a brilliant analog to this, okay? At any given temperature, there's a plot you can make of how many particles have what speed of vibration.
Right.
It will slowly go up, it'll peak, and then it'll come down again. Raise the temperature.
Now we just went from Inner Sandman to like Pantera.
All right.
And we're just going crazy.
Now watch. This plot has most people with this vibrational energy.
Right.
I raise the temperature, the peak vibrational energy goes
Slides across.
Slides.
Right.
It slides.
Right.
I still come down here to zero. This kind of thins out. Everybody's moved here, and we still have the people at the far end.
Right.
You can derive the temperature of the gas from what the shape of this curve is. And in fact, for the calculus weenies out there, if you is that you?
No.
You quickly
I was
recall.
I'm a calculus. Where? Please, no.
Okay, for the calculus weenies out there, if you take the first derivative of this curve and set it equal to zero, that is the place where the curve has zero slope.
Okay.
That's the top of the curve.
I don't know why that made sense to me, but that makes sense.
That makes complete sense.
Yeah.
So you can do the math on this equation and find out where it has zero slope, and that's the peak of the curve.
Gotcha.
Okay, so now watch. You ready?
Go ahead.
Okay. I have a swimming pool.
Right.
What's the temperature? Let's call it 80 degrees.
All right.
Okay, not too hot, not too cold.
Yeah. I mean, it's wintertime.
Okay. At what temperature does water boil?
212?
We are in Fahrenheit, correct.
Fahrenheit, 212.
So clearly the pool is not boiling.
Nowhere near boiling. Right.
But.
Nowhere near zero either.
Correct. But the water evaporates.
That's right.
How does it evaporate if it's not boiling?
That's right.
If all the water is not at 212 degrees, how are any molecules of water coming off the surface? At the far end of the Maxwell velocity distribution,
those excited people.
Those
are jumping out of the mosh pit.
They're popping out of the mosh pit.
I gotta go. I'm done.
No, Chuck.
By the way, that's freaking amazing.
It's freaking amazing. So in a mosh pit example, you would watch the occasional person just leap out.
Right.
But that opens up a hole. Other people come in and take that space, and then they leap out.
Wow.
So most of the water is not evaporating.
That's right. Only the excited people over there at the very edge.
And there's always an edge,
of course,
of this distribution.
That's so cool.
So obviously, the hotter this is, the more you're going to evaporate.
Right.
And then the colder it is, it evaporates slower.
Slower and slower.
Slower and slower. Right. Because there aren't many that are at that extreme.
You're de-exciting the whole crowd.
The whole crowd. But there's still a bit on the edge. It just happens slower.
Wow.
Now, it's not Maxwellian, but the same applies. Let's go down to ice cubes.
Okay.
Okay? I make a fresh, brand new brand ice cube.
Nice.
Okay?
We're having scotch, I see.
Okay. I drink mine straight. I'm a straight guy.
Good for you.
So there's an ice cube.
All right.
Is it at absolute zero?
No.
No. It's at freezing or a little less or whatever your freezer did it.
Exactly. Right.
Which means the molecules still have vibrational energy.
Right, exactly.
Okay. And they're not all vibrating at exactly the same rate.
Mm-hmm.
Take a perfectly shaped ice cube, put it in the back of your freezer, and come back a month later. The edges are all smooth.
Right.
And the ice cube is smaller.
Right.
The ice cube was evaporating.
Wow.
Even though it was frozen, because there's always motion everywhere at all times.
Damn. That's pretty cool.
It's pretty dope. Right. But the Maxwellian distribution, that's what feeds the evaporation of anything. That's if all the molecules have the same mass.
Okay.
Okay? If I have a mixture of masses, okay, so like our atmosphere.
Right, because it's
oxygen
and oxygen.
They're close in mass.
Argon.
Or a little bit of argon. They're close in mass. Whatever is your mixture of molecules, the full mixture, if it's mixed, will have this shape. However, the lower mass molecules will be preferentially found
at the more
excited side of the curve.
That makes sense.
Okay.
They're the little like squirrels on meth.
Okay, yeah, because a bigger one hits it. Yeah, so they are much more reactive to this motion, even though they're all on the same curve.
Yeah.
Okay, so now watch. If I release some helium at the bottom of our atmosphere, if one of those Macy's Thanksgiving Day balloons pops and the helium gets out, helium is way lighter than oxygen, argon, nitrogen.
Right.
It'll be vibrating way faster. You know how fast? It'll be vibrating so fast, its speed will be greater than the escape velocity of Earth. So the helium will just work its way up the atmosphere until it gets to the top of the atmosphere and it's gone forever.
Deuces. See you later.
Gone, because it had the highest speeds of this curve.
This guy was a genius.
And let's call that evaporation. Though it's technically not, because it's involving gravity as well. Right. But if you lose those highest moving particles, the average temperature drops. So evaporation is fundamentally a cooling process.
That's very, very cool.
Just saying.
That makes sense.
Yeah. There it is. That is the Maxwell distribution of velocities. No one talks about it.
No joke. I've never heard of it. Kidding me?
Yeah.
Wow, this is really cool. God, I got to tell you, science is really interesting.
Really? You know, we should start a podcast.
Something with this.
So that's another explainer, Chuck.
That's a great one. I got to tell you, when you said Maxwellian distribution of velocity, I went, well, he done jumped the shark now. We finally did it. We killed StarTalk. But that was truly, truly interesting.
Yeah, well, thank you. Yeah.
And by the way, Now I really understand evaporation.
Yeah. That's basically
That's basically what evaporation is happening.
It's basically evaporation. And one thing I left out just to complicate things.
Go ahead.
You could do Maxwell's equations in each coordinate. In the X direction, the vibrations in X, vibrations Y, and vibrations in Z.
Right.
And not always are they equally spread into those coordinates. And those are weirder gases that have different preferential vibrational modes. So if you just say Maxwellian distribution of speeds, it doesn't care which orientation it is.
Just velocity, you got to add the direction.
Velocity has direction, speeds. So that's the fuller story of what that is. Badass dude.
That is
19th
total
century.
badass.
There it is.
Look at that. How come we're not that smart today? What happened?
We're arguing about whether Earth is flat.
That's right.
That's where our brain power is going.
This guy is like coming up with equations that tell you like the excitation of molecules in fluids. And we're talking about we never went to the moon and the Earth is flat.
All right. That's a wrap. This has been another explainer. Explainer edition? What do we call it? Another StarTalk explainer with Neil and Chuck.
Yeah.
Chuck, always good to have you.
Always a pleasure.
Till we meet again, as always, keep looking up.